Hello all, once again welcome to the LJ Institute of Engineering and Technology. Let's start with the subject Mathematics 2 and chapter same series solution of ODE. Today's topic is Roderick formula. As I told in previous lecture that we have another formula which also can help us to find Legendre polynomials. Okay, so for that we have to understand what is Roderick formula and we have to derive, we have to give the proof of Roderick formula. That will give you some 2 3 new also concept. Okay, so let's start with the proof of Roderick formula. First, what is Roderick formula? So this is our Roderick formula. Pn of x is equal to 1 upon 2 raised to n by n, into n factorial into d raised to n by dx raised to n of x square minus 1 whole raised to n. That means nth derivative of this term x square minus 1 whole raised to n. Okay, so how we can prove this? So let's start with the first proof of this. So we'll take this is equal to our y function and we'll just differentiate this n time. But it is possible? No, for that we will just have a one trick. So let's start with this equation number 1 y. Now first differentiate with respect to x one time. So we have y, differentiation of y is y1, differentiation of n, this term we know that power forward and 1 power minus, and derivative of base, that means chain rule. Now we can simplify this by taking these two terms together. So we have 2nx. Okay, and we can write this as x square minus 1 raised to n into x square minus 1 raised to minus 1. Means same addition of power, so n minus 1. So we can write this and this goes to the denominator. So we have this form, and now we can take this x square minus 1 on the left hand side. So we have this format, that x square minus 1 into y1 into n to n x, and this is our y. We know that this is our y, equation number 1. Now again we will differentiate this with respect to x. So we have product rule of these two and product rule of these two. 2n is constant. So by using product rule, first x square minus 1 as it is, derivative of y1 is y2. Now y1 as it is, derivative of this x square minus 1 is 2x. Now 2n constant as it is, and product rule. So x as it is, derivative of y is y1 plus y as it is, and derivative of x is 1. So we have this. Now by simplifying this, we have, by simplifying and taking these two terms on the left hand side, so we have this x square minus 1 y2, 2x y1 minus 2nx y1 minus 2ny is equal to 0. Now we will take this y1 common from this two term. So we have this 2x and y1 common, 2x y1, so 1 minus n. And now we can take minus from this all this term. So this, sorry, this is our equation number 2. We will use this equation for next derivative, that means nth derivative. Okay, because we need nth derivative of this term. Okay, so now we will just write down this equation number 2 here, and now we will start with the second derivative. So differentiating equation number this 2 n times by using Leibniz theorem. What is Leibniz theorem? So Leibniz theorem is given by this formula. Okay, if we have y is equal to u and v, both we have two function multiplied together. Okay, and if you want to differentiate this n time, so we have formula is this y n is equal to nc0, this u as it is, and nth derivative of v, nth derivative. So you have to consider the term whose nth derivative is known. Okay, so you have to just write down the nth derivative of v and plus nc1, first derivative of u, and 1 minus derivative. We have nth derivative of v, we have to just minus 1, taking n minus 1 instead of n in that nth derivative. And nc2, second derivative of u, again 1 minus from the n, and so on till ncn. We have nth derivative of u and we have v. Okay, we have v back. Okay, so this is our Leibniz theorem for nth derivative of any equation. What is the NC0, NC1, NC2, NCN? We all are familiar with that values. Okay. Now we will use this for this equation number 2. So this is our u and this is our v. So we will take u such as its derivative vanishes after 2, 3, 4 terms. Okay. So this is our u and this is our v because we know the nth derivative of y2. Okay, nth derivative of y is yn. So nth derivative of y2 is yn plus 2. Okay, so nc0 u as it is, nth derivative of y2 is this, same plus nc1, first derivative of this is 2x and one minus derivative from this, so we have n minus n plus 1 minus 1, so n plus 2 minus 1, that means n plus 1, then nc2, one more time derivative of u and one minus from this, so we have yn. Okay, so you have to follow this. This is your u and this is v. So u as it is, derivative of u, derivative of u. Okay, again, and nc0, nc1, nc2, and the derivative of y2 minus 1 gives us this. Okay, similar way we'll use this constant and we'll use same concept for this. X is our u, y1 is our v, so we have this as it is. Okay, nc0, now 2x is our u as it is, and nth derivative of y1, nth derivative of y1 is yn plus 1, so we have this. Now nc1, derivative of 2x is 2 and 1 minus from this, so we have yn, and 2n is constant and nth derivative of y is, you know, that yn. So this is our Libny's theorem for nth derivative, okay, that you have to remember. Now by simplifying this, so for simplifying this we need to write this equation again. So I'm just write down this equation again. Now we'll just simplify this. What is the value of nc0? 1. What is the value of nc1? Is n. What is the value of nc2? N minus 1 by 2 factorial, and we'll just put here also. So we have this value nc0, nc1, nc2. Now we'll just simplify, or we'll just expand the bracket. So this term as it is, this term as it is, and we'll just cancel out, and opening this bracket, n square y2 minus n square yn minus n yn. Now again this simplify 1 into this, n into this, and similarly 1 into this, n into this, and this as it is. So we have this term. Now you can see that some terms are cancel out. This cancel out, and second is 2n yn is cancel out. So remaining term this, and subtracting this from this, and this term is single. Okay, so we have first term as it is, this n plus 1 term as it is, and you can subtract this 2, so we have this, and this yn is yn as it is. Now we can take common from this 2 term, so first second term as it is, and we can take minus n and yn common, so we have n plus 1 in the bracket. Okay, now we can take minus from this, each and every term, minus from this, and minus from this gives us this equation. And now you can observe that this equation is exactly look like Lysander equation. If we put this yn as v, okay, so we have this equation, and if we put yn, this is our yn, nth derivative of y is v, so we have this as it is, and this become v2, that means second derivative of v, this as it is v1, that means first derivative of v, and this is our v. So this is exactly look like our Lysander equation, and we know the solution of Lysander equation is this Pn of x. Okay, this is the finite solution of Lysander equation. So we can say that v is equal to this. Okay, so v is equal to this is the solution of Lysander equation. Okay, and we can write Pn of x is equal to same to this. This is our v, because we are supposed. This is our equation number 3. Now we will find the value of c. How we can find the value of c? So again we will start with the y. So we know that what is the y? X square minus 1 raised to n. Now I can factorize this x square minus 1 as x minus 1, x plus 1. So we have x minus 1 whole raised to n, x plus 1 whole raised to n. Now what we will do? So we'll consider u and v. So we'll take u this and v this, or instead of this any you can use u and v. Okay, I'm using this is u, this is v. So we have same Lysander theorem. So nc0 u as it is, nth derivative of v plus nc1, first derivative of this is this, and 1 minus of this. Okay, 1 minus derivative, not from this. Okay, similar way we have so on up to nth derivative. So ncn and nth derivative of this, and simple this v as it is. Okay, so now by simplifying this we have 1 as it is, and nth derivative of this become n factorial. We know that nth derivative of x raised to n gives us n factorial. Same for this x minus 1. Now this is n, this is n becomes n square, this term as it is, and n minus 1 derivative of this, and so on. We have last this as it is, and nth derivative of this is n factorial. Now we'll just write down again that term, and we'll put x is equal to 1. If you put x is equal to 1, so this become at x is equal to 1, 2 raised to n into n factorial, because if we put n, x is equal to 1 here, and each and every term becomes 0. Okay, so we have this, and we'll put x equal to 1 in equation 3 also. So equation 3 was this one. Equation 3, we have, this is our equation number 3. So we will put x equal to 1. So Pn of 1 C, and this term value at x is equal to 1. So we know the value of this is this, and we know the Pn of 1 is always, Pn of 1 is always 1 by Lysander polynomial. Okay, so we have C is equal to 1 upon 2 raised to n by n into n factorial, and we'll put this in equation number 3, and this gives us the Roderick formula, hence the proof. So this is the entire proof of Roderick formula. Now after finding this Roderick formula, that you have to remember compulsory. So you have to remember two formula for Pn of x, the general formula of Lysander polynomial, and this is Roderick formula. Okay, that we have to remember Roderick formula. Okay, this one. Now we have, by using Roderick formula, we can find Lysander polynomials for n is equal to 0, 1, 2, and 3, and so on. So if you put n is equal to 0, so we have 2 raised to 0, 0 factorial, and 0 derivative. That means simple. And this is our 0. So we have this 0, 0, 0, 0. So this is 1. This cancel out, and this is 1. So P0 of x become 1. Same answer. You will get same answer as from the general formula of Lysander polynomial. Okay. So now we will put n is equal to 1. So we have 2 raised to 1, 1 factorial, and 1, 1. That means 1 derivative of x square minus 1 raised to 1. Okay. So 1 derivative of this is 2x. So by 2 cancel out 2, 2, we have b1 of x is equal to x. Similar way, if we put n is equal to 2 in this Roderick formula, so we have this 2, 2 factorial, 2, 2, 2, second 2 time derivative of this. So 4, 2s are 8. If we differentiate this first one time, so one derivative is there as it is, and 2x square minus 1 2x. 4 cancel with this, so we have 2, 1 by 2, and second derivative of this multiplying this x in this bracket. So second time derivative of this is 3x square minus 1. So this is our P2 of x. And similar way, by using Roderick formula, we have this P3 of x, P4 of x, P5 of x, P6 of x, and so on. As I told, we have to remember all these values. Okay, so just remember all these values. Just write down 2, 3, 4 times, so you can understand, you can remember two formulas: general formula for Lysander polynomial and Roderick formula, and how to find the value of P0 of x, P1 of x, P2 of x, and all. Okay, now we have this example by using that Lysander polynomials. So that x cube is equal to 2 by 5 P3 of x plus 3 by 5 P1 of x. So we know the value of this and this. Okay, so we'll start with the right hand side. So in right hand side we will put, okay, so first we'll write down the value of P3 of x and P1 of x, that already we know, and then we will write down the RHS and we'll put the value of this 2, and expanding we have the final left hand side. Simple. So for that, I know I told you we have to remember this value of P0 of x, P1 of x, P2 of x, P3 of x, P4, P5, P6, and so on. Okay, now we have this example. express the polynomial this in terms of Lysander polynomial. That means in terms of this P0 of x, P1 of x, P2 of x. Okay, but here we have maximum power x cube. So we have x cube is contained in P3 of x. So we start with the P3 of x. So we have value of P3 of x is this. From this we can make x3 subject. So we have x3 is equal to x raised to 3 is equal to this. Now x square will be obtained from the P2 of x. So we will make x square subject from this. So we have this and x from P1 of x and constant, that means 1, 3 into 1. So we have P0 of x. Now we'll write down this function. Now we'll put the value of all this x raised to 3, x raised to 2, x raised to 1 and here 1. Okay, so we have this value, right? And now we know the value of x also. We have P1 of x and constant we have P0 of x. So we will put this value and we will expand also this bracket. So we have this. Now we are collecting same Lysander polynomial. Okay, so we have P3 of x is single, P2 of x is also single, but P1 of x we have two term. So we will take together 3 by 5 minus 1. So we have minus 2 by 5 and for this P0 2 by 3 minus 3, so we have minus 7 by 3. So this is the expression of this polynomial, this given polynomial in the term of the center polynomial. Okay, so these are the example, two type of example that you have to solve by yourself, and these are the simple DIY that you have to solve by the previous examples method. That first example show that x raised to 4 is equal to this. So start with the right hand side, put the value of P4x, P2 of x and P1 of x, P0 of x. For that you have to remember all this value. Second example just previous. Third example is same as first example and fourth example same as second example. So we have four different example in example number 4. Okay, so these are the examples that we have to solve by these previous examples method. Okay, so thank you for today's lecture. We will see you soon with next topic, next lectures of this Lysander. Okay, so thank you very much.